The acceleration of a particle p at time t is given by a of t is equal to 60I centimeters per second squared. The initial displacement and velocity are negative I plus j plus k centimeters and k centimeters per second. Find the position vector of p when it crosses the yz plane. Okay, so what we're given here is that a is equal to 6t0, 0. We're given that r, this is r of 0, is negative 1, 1, negative 2, and the initial velocity, v of 0, is 0, 0, 1. So, velocity at time t is given by integrating the acceleration. So for that, we're going to get 3t squared plus a constant. Then with the two zeros, we're just going to get constants, like so. And the fact that the initial velocity is 0, 0, 1 tells us that C1 is 0, C2 is 0, and C3 is 1. So that is going to give us that V of t is 3t squared, 0, 1. To get the position vector at time t, we integrate the velocity. And so that is going to be t cubed plus c4. And then we're going to have c5 and t plus c6. That was integrating the 1. Now, because we know this, that tells us c4 is negative 1, c5 is 1, c6 is negative 2. So we get to t cubed take away 1, 1, and t minus 2. Now we're interested in the yz plane. Now if we think about some axes here, let's just say this is x, y, and z. The yz plane is this plane here where x is equal to 0. So if x is equal to 0, that means t cubed take away 1 is equal to 0, which means t is equal to 1. So r of 1 is equal to, so we'll have 1 cubed take away 1, which is 0, then we've got 1, and then we would have 1 take away 2, which is negative 1. We now want to find the velocity of p as it crosses the xy plane and state the angle the velocity vector makes with the xy plane. Okay, so the xy plane means z is 0 in the same sort of argument we used here. And that means that t is equal to 2. So, v of 2, going back to here, 2 squared is 4 times 3 is 12. So it's going to be 12, 0, 1. And that would be in centimeters per second. I should have said centimeters for this one. And then if we want the angle with the xy plane, it's in the xy plane, and it's going 12 that way and 1 that way. And so the angle that it makes is this angle here, call it theta, and theta is going to be the inverse tangent of 1 divided by 12, which is about 4.76 degrees. We now want to find the magnitude of the change in displacement in the first 2 seconds. Well, we worked out that r was t cubed minus 1, 1, t minus 2. So r of 0, well, we were given that in the question, negative 1, 1, negative 2. R of 2 is going to be 8 take away 1 is 7, then 1, and 2 take away 2 is 0. So the change in displacement is going to be, well, we're going negative 1 through to 7, which is 8, no change in y, and negative 2 to 0 is 2, so it's just going to be the square root of 8 squared plus 2 squared, which is the square root of 68, which is about 8.25 centimetres. Actually, that's not really the change in displacement, is it? This one is the change in displacement. I've just worked out some extra information that I didn't need there, because the displacement is a vector. So our answer is that one. And if we wanted the distance between those 2 points, it would be this. So I didn't actually need to do that, but I'm not going to re-record. Find the distance travelled along the path in the first 2 seconds. Well, it's going along a curve, so it's not going to be this distance between those 2 points. And we had r of 0 and r of 2, so it's not going to be a straight line. There's going to be some sort of curve that it goes along. We want the length of that. So if we want distance, we're going to do the integral from 0 to 2 of the modulus of the velocity dt. So that is going to be the integral from 0 to 2, and our velocity vector was 3t squared 0, 1. And so that is going to be the square root of 9t to the 4 plus 1. And we can calculate that on the class pad. And that gives me 8.63 centimetres, correct to 2 decimal places. And actually, it's now worthwhile having worked this out, because we can see it's just a bit longer, which probably indicates that we've got it right.